Today we will be dealing with these four Maxwell's equations. The full name of Maxwell is James Clerk Maxwell. He was a Scottish physicist who compiled these four famous equations which unified electricity, magnetism, and light into one theory of electromagnetism. They explain how electricity and magnetism are deeply connected with each other and can produce or induce each other when they change with time. Remarkably, these equations also predict the existence and speed of light, which revolutionized physics forever. Now, in order to understand them, you simply have to understand the concept of scalar fields, vector fields, divergence, and curl, and that's it. After getting a hold of these ideas, Maxwell's equations will feel like a piece of cake to you. I've actually made a detailed video on these topics earlier, but for your convenience, I'll quickly show the relevant part here as well. If you haven't seen them, watch them fully, and if you already have, you can simply jump ahead to this timestamp. A scalar is simply a number. It has magnitude but no direction. Examples of scalars are temperature, mass, time, or height. For instance, if the temperature at a place is 30 degrees, that number alone fully describes it. There is no direction involved. Then a vector has both magnitude and direction. For example, wind blowing with a speed of 10 units toward the east is a vector. The number 10 tells you how strong it is, and east tells you which way it points. Next, a scalar field is formed when a scalar value is assigned to every point in space. For example, suppose at the point with coordinates 4, 3, the temperature is 217 degrees Celsius, and at the point 8 and 1, the temperature is 83 degrees Celsius. Each point has a single number attached to it. That collection of numbers spread over space is called a scalar field. Then a vector field works the same way, but instead of a single number at each point, we assign a vector at each point. A classic example is wind flow. At every coordinate in space, the wind has a speed and a direction. So at one point, the wind might be blowing slowly toward the northwest, while at another point, it might be blowing faster toward the southwest or northeast. The collection of all these vectors distributed in space forms a vector field. Now, to describe scalar fields mathematically, we use scalar functions. A scalar function takes coordinates as input and outputs a single number. For example, a function might take x and y as input and give you a height value like f of x, y equals x squared plus y squared, which outputs a single number like 13 when x is 3 and y is 2. So, the height at 3, 2 is 13 units. Then, at origin, height is 0. Then, maybe at 1, 3, the height is 10 units. Now, if we want to draw this in 3D, do one thing. At each point in the xy plane, whatever is the value of the height, make a segment of that length rising upward from the plane along the z-axis like this. This way, if you plot it in 3 dimensions with x and y as x and y coordinates and z representing the value of the function, it creates a smooth surface shaped like a giant bowl or pit centered at the origin. Then, to describe vector fields mathematically, we use vector functions. A vector function takes coordinates as input and outputs a vector with components in different directions. For example, v of x, y equals a column vector where the first entry is 2x and the second entry is y. If we evaluate this function at the point 1, 3, the output is a vector telling you to move 2 units to the right and 3 units up. At the point 3, 4, the output is a vector that tells you to move 6 units to the right and 4 units up. This means the further you move away from the origin, the longer and stronger the vectors become, because the magnitude of the output increases with the distance of the coordinates. Now, we introduce a very important object called the del operator. It is written as a downward-pointing triangle and pronounced as Del. The del operator is a vector-type operator that performs partial derivatives in different directions. In 2 dimensions, you can think of it as having one component that differentiates with respect to x, and another that differentiates with respect to y. Because it has multiple directional components, it behaves like a vector. When we try to apply the del operator directly to a vector field, we must be careful. Both the del operator and the vector field are vectors. There are only 2 meaningful ways to combine 2 vectors, either the dot product or the cross product. If we use the dot product, we get divergence. If we use the cross product, we get the curl. First, let us talk about divergence. Divergence is defined as the dot product of the del operator with a vector field. The result of divergence is always a scalar field. The word divergence literally means spreading out. To build intuition and understand it mathematically, imagine a vector field V of x, y equals a matrix where the first entry is x and the second entry is y. On a graph, it will look like this. Say this vector field represents the flow of a fluid, such as air or water. At each point, the vector tells you how the fluid is moving. Here is the del operator. Now, take the dot product of these 2 vectors. It will give us divergence of this vector field. We get this plus this. The partial derivative of x with respect to x is 1, and the partial derivative of y with respect to y is also 1. When we add them together, we get a constant divergence of 2. Now, imagine placing a tiny square region in this flow and watching what happens to particles inside that region. If more particles leave the region than enter it, the density or the number of fluid particles packed inside this square region decreases. In this case, because the vectors point outward and get longer as they move away from the center, more particles leave the region than enter it, and thus the density inside decreases. This means the field is spreading out there, and the divergence is positive. Next, consider a vector field where the first entry is minus x and the second entry is minus y. Here, the partial derivative of minus x with respect to x is minus 1, and the partial derivative of minus y with respect to y is also minus 1, giving us a divergence of minus 2. In this flow, all the vectors point toward the origin. If more particles enter our tiny square region than leave, the density increases. This means our vector field is converging, and the divergence is negative. Then let us look at a field where the first entry is minus y and the second entry is x. On a graph, this vector field will look like this. The partial derivative of minus y with respect to x is 0, and the partial derivative of x with respect to y is also 0. So the divergence is exactly 0. In this scenario, the fluid is simply rotating in a circle. If the number of particles entering the region equals the number leaving, the density stays the same, and the divergence is 0. This tells us that even though the fluid is moving, it is not spreading out or packing together. We could have also taken the vector field as constant, like this, representing a steady stream of water flowing uniformly to the right at a constant speed. Every single vector in the entire space is identical in length and direction. Because the fluid is moving at the exact same speed everywhere, the amount of water entering through the left side of the square is identical to the amount of water exiting through the right side. If the number of particles entering equals the number leaving, the density inside the square stays the same, and thus the divergence is 0. Amazing! Now, let us move to curl. Curl is obtained by taking the cross product of the del operator with a vector field. Unlike divergence, curl produces a vector field as its result. Curl measures rotation rather than spreading. To understand curl intuitively, imagine placing a tiny paddle wheel in a flowing fluid described by this vector field. If the fluid makes the wheel spin, then the curl is non-zero. To find the curl of this vector field, The cross product of this field with the del operator is calculated by finding the determinant of this matrix, where the top row contains the unit vectors I, j, and k. The second row consists of the partial derivative operators with respect to x, y, and z, while the bottom row contains the actual components of our vector field. It turns out to be this. For this specific field, the partial derivative of x with respect to x is 1, and the partial derivative of minus y with respect to y is minus 1. When we subtract minus 1 from 1, we get 1 plus 1, which equals 2. Now, because the curl is 2, the flow will rotate the paddle wheel. Conversely, if the curl value were minus 2, the paddle wheel would spin at the same speed, but in the opposite direction. If the wheel does not spin and only moves straight, then the curl is 0. So curl tells us whether the field has a tendency to rotate around a point. All right, now that you understand vector fields, divergence, and curl, you can see here that Maxwell's equations are all about either the divergence of electric or magnetic fields or the curl of electric or magnetic fields. Okay, let us first start by learning what an electric field E is. Imagine you have a small point charge, say Q. We know that other charges around this charge either get pushed away or pulled toward it because of the electric force, right? So electric fields are vector fields, like imaginary arrows we draw in space to show the direction and strength of the electric force that a positive test charge would feel if placed there. For example, around a single positive charge, electric field lines spread out evenly in all directions like rays from the sun, showing that the force pushes other positive charges away equally in every direction, and the strength of that field decreases as you move farther away from the charge. Similarly, around a negative charge, the electric field lines all point inward toward the charge, showing that it pulls a positive test charge toward itself from every direction. We use the letter E to represent this electric field. This vector field doesn't really exist physically, as it is just a visual tool to help us understand where the electric force points and where it is strong or weak. Great! Now, let us understand the magnetic field B. Imagine a simple bar magnet like the one you might have played with in your childhood. Even when the magnet is just lying on the table, it influences the space around it. If you bring a small piece of iron or another magnet near it, you will notice that it turns and aligns itself in a certain direction. This happens because this bar magnet creates a magnetic field around it. Just like electric fields, magnetic fields are vector fields, meaning at every point in space, we imagine an arrow showing the direction and strength of the magnetic influence there. Around a bar magnet, the magnetic field lines look like they come out from the North Pole, curve through space, and enter the South Pole, forming smooth loops around the magnet. These arrows show the direction a small piece of iron would move, or align if placed at that location. We use the letter B to represent this magnetic field. If this is clear, then let us move on to our first Maxwell's equation. It was discovered by Carl Friedrich Gauss in the early 19th century while studying electric fields produced by charges. Later, Maxwell included it as one of the 4 fundamental equations of electromagnetism in his theory. Divergence of the electric field E equals rho divided by epsilon 0. It is also called Gauss' law. Consider an electric field of a positive point charge like this. Gauss discovered that the divergence of the electric field is directly related to the presence of electric charge at that point. In the equation, rho represents charge density. Charge density simply means how much electric charge is packed inside a volume, or simply Q over volume V. The term epsilon 0 is a physical constant called the permittivity of free space, which tells us how electric fields behave in an empty space. Just consider it as a constant. So what the equation is really saying is that some accumulation of electric charges over a certain volume is going to create an electric field around it. In fact, the amount of electric field spreading out from a point, which means the divergence of E, depends on how much charge is present there, which we measure using the charge density ρ. A net positive charge behaves like a source or a beginning because the electric field arrows radiate outward from it in every direction. A net negative charge behaves like a sink, or an end because the electric field arrows converge inward toward it from all directions. Also, the term epsilon zero tells us that the electric field produced by the same charges can change depending on the material present. So keep in mind that the first law says that electric charges create electric fields. That's it. Now, let us move on to our second equation, which is kind of similar to the first one, and it says that the divergence of B equals 0. This was also discovered by Gauss, and it is called Gauss's law for magnetism. This law tells us that magnetic monopoles do not exist. We cannot find isolated north poles or isolated south poles in nature. They always exist in pairs called dipoles. So even if you cut a bar magnet, each piece will again form its own north pole and south pole. So there's no such thing as a magnetic charge which creates a magnetic field. This is because magnetic field lines have no beginning or end, as they cannot start at a north pole and stop at a south pole in the way electric field lines start on positive charges and end on negative charges. Instead, magnetic field lines are continuous and must form closed loops, or, in some idealized uniform cases, they extend infinitely as straight lines, but those can be thought of as closing at infinity. So around a bar magnet, magnetic field lines emerge from the North Pole, curve through space, enter the South Pole, and continue inside the magnet back to the North Pole, completing the loop. Then around a current-carrying wire, the magnetic lines form circular closed loops encircling the current. Then, in a uniform field, like inside a very long solenoid, magnetic lines appear straight and parallel, but conceptually, they still form extremely large closed loops. Okay, enough of divergence. Now, let us talk about curl of both these fields. See, an electric field can be created from two completely different things. In the first law, we stated that electric charges create electric fields. This third law says that changing magnetic fields creates electric fields. That's it. This is the gist of third law, and it was discovered by Michael Faraday in 1831. Therefore, it is also known as Faraday's law of induction. This equation says the curl of electric field E equals minus rate of change of magnetic field B with respect to time. We know that curl measures local rotation, or spinning, of a vector field. So, this equation says that if the magnetic field changes with time, it produces a rotating electric field. Imagine a magnetic field pointing out of the page. Now suppose the magnetic field is increasing, so an electric field appears circulating around it. This is how the vector field of the circulating electric field will look like. Now if you take a metal ring and place it in that changing magnetic field, the circulating electric field pushes charges around the ring. As a result, current starts to flow in the ring even though no battery is attached to it. This is called induced current. This phenomenon is what we call electromagnetic induction, and it is the basic principle behind generators, transformers, and many electrical devices. That is simply mind-blowing, isn't it? Now let us move to the fourth and final equation, which talks about the curl of the magnetic field. First, a magnetic field can be created by moving charges. This was first discovered by Hans Christian Ørsted in 1820, when he observed that a compass needle deflects whenever electric current flows through a nearby wire. The term J in the equation represents current density, which simply means electric current flowing through a cross-section area at that point in space. So whenever electric charges move through a wire, they produce a circulating magnetic field around them. It was studied and mathematically formulated by André-Marie Ampère. So this part of the equation is called Ampere's law, and even the unit of electric current, the ampere, is named after him. But later Maxwell realized that this was not the complete story. He added the second term, which involves the change of electric field with time. This means that even if no charges are moving, a changing electric field can still create a magnetic field. So according to this equation, circular magnetic fields can be produced either by electric currents or by changing electric fields. So this fourth equation is also called Ampere-Maxwell law. This variable μ0, like epsilon 0, is a physical constant called the permeability of free space. This also depends upon the material present around the field. That is out of this world. Now, something very interesting happens when these two equations work together. According to the third equation, a changing magnetic field creates circulating electric field loops. But now, those electric fields can also change with time. And according to the fourth equation, a changing electric field creates circulating magnetic field loops. So we get a chain reaction. Changing B creates rotating E, and changing E again creates rotating B. This process keeps repeating, and the two fields continuously regenerate each other, forming a self-sustaining cycle in space. Instead of staying at one place, this wave or the disturbance of electric and magnetic fields starts moving forward through space. The electric field oscillates up and down, while the magnetic field oscillates sideways, both perpendicular to each other and to the direction of motion. Maxwell calculated the speed of this traveling wave using his equations, and found that the speed of this wave equals 1 divided by the square root of μ0 times epsilon 0. When he substituted the known values of these constants, the speed came out to be a constant of about 3 times 10 to the power 8 meters per second, the measured speed of light. From this, Maxwell made an incredible discovery. Light itself is an electromagnetic wave. Many years later, Albert Einstein used this very idea as a starting point for developing the theory of special relativity. Since Maxwell's equations predicted that the speed of light must always be the same, Einstein built an entirely new framework of space and time around this principle. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So go!